Okay, so last time we were talking about energy, chapter 10. We talked, again about exothermic and endothermic. We also looked at some energy diagrams. And when we look at an energy diagram such as this, where we see, again, our reactants are higher in energy than our products, there's going to be a net release of energy in this process here to allow those reactants to get down to our products, so exothermic in this case. And that is opposite what we see sort of over here. Our reactants are lower in energy than our products, so there's going to be a net sort of increase or absorption of energy to be put in there to allow those reactants to get up to the products. The other part of this sort of diagram that we talked about, or a couple of parts, is this hill that the reactants has to climb to get to the other side. That is the activation energy. And that is the minimum amount of energy that's required for a reaction to basically occur. And as we talked about, it does play a role in how fast or slow reaction will take place. So as we talked about, if you have a fairly large sort of activation energy or hill that those reactions has to climb to get to the other side, it's going to probably take a little bit longer than if you had a sort of smaller activation energy or hill that they have to climb to get to the other side. Usually we'll see an increase in the rate of the reaction because of that. Now, the difference actually in the energy of our reactants to our products is another sort of thing that we were talking about, which is, the difference in energy between those two, if I could draw straight lines, is what's known as the delta H here of the reaction. And the delta H, one way that you could calculate, as we were doing there towards the end, is to take the delta H value of all the products and subtract it from the delta H value of all the reactants. And typically speaking, if you're just given an equation and you're asked to calculate the delta H or the change in enthalpy, which is what that is, those are typically table values. So you would go to a table basically and look up all the values for all your reactants, all your products, and you would add up all the delta H's for your products and subtract them from delta H's of reactants. Remember, though, when you do that, you do have to take into account the coefficients. So when you go to that table and you do this calculation, you would do something like the delta H in this example of our products, 3 times the delta H value for C that you would find in the table. You would then subtract it from 2 times the delta H value for A that you would find in the table, plus the delta H value for B, because the coefficient here is 1. So that's another important thing, that when you go to that table or you use those type of values, that you do have to take into the mole-to-mole relationship or the stoichiometry of the equation into account when you do that. Also, you want to always make sure that when you look up in those tables, that you find what you're looking for and it's in the right state, solid, liquid, gas, aqueous, whatever it may be. And typically speaking, anything that is in its standard state uncombined by itself will have a delta H value basically of 0 in a lot of those cases. So we can do this, we could calculate this, we could look at our graph here, but ultimately, if our delta H value is negative, that usually is an exothermic reaction. And again, if we see a positive value for delta H, that's an endothermic reaction. And again, the number really doesn't matter all that much. It's really just the sign here. And usually with energy, that's the case. It's really the sign that's important to determine whether or not something's going to be sort of exothermic or endothermic. Any questions on any of that stuff there? I think we talked about last time. Okay, so we did one example at the end there. So I think we got one more. So why don't we do this one? Calculate the delta H for this reaction using the values that you would find in a table here. Okay, let's take a look. So once again here, we're going to, by the way, if you find these in a table. So we'll do our delta H here. Going to be, again, our products minus our reactants here. And we do want to kind of sum up all the products and reactants and take them together. So starting on our product side there, we have a 12 CO2. So we do need to take 12 times the value of CO2 that we see in the table, which is minus 393.5 kilojoules. We will then add it to our other product, and there's 6 of those. So we do need to take 6 times the value for water that we find in this table. And that's going to pretty much take care of everything we got going on the product side here. We're then going to subtract it from everything on the reactant side. So on the reactant side, we have 2 of our benzene there. So 2 times 4904. And in this case, we have 15 of them, but that is oxygen in its natural state, which, as you will typically find on these tables, will have a value of 0. So we'll do the math there. We'll make 12 times minus 393.5. We'll add it to 6 times negative 286. We then will subtract it from 2 times 4904, basically. And I'll get us something here in the ballpark of minus 6536 and kilojoules. This reaction would be endothermic or exothermic. It would be exothermic, as overall here we got really a release of energy, and we know that by the negative sign, and it will be exothermic. Any questions on how to calculate change in enthalpy? Yeah, it does. So I don't know how careful I was on this one, but you should. So we're multiplying here, but we're really adding. So really this should come to a whole number, right? Based off of this one, basically. And over here, we basically are multiplying, and that's 2 decimal places and 1 no decimal places. So it probably should end up in the end as no decimal places. So the last thing that we did basically is subtract the 2, right? The products minus the reactants. So we should end up with really no decimal places on the first one, minus 2 decimal places on the second one. So we should end up with no decimal places. So I guess I did good, yeah. The work that you would need to show would be what's on the bottom here. Yeah. This would be given to you in this type problem, the actual equation, if that's what you're asking, would be given to you. So you could go look up the values and stuff like that. Yeah. Other questions? Yeah. So those would be more probably like exact numbers, right? Rather than sort of a definition or something like that. So the 12 and the 6 and all those, we wouldn't necessarily worry too much about those. It's really kind of the numbers inside that we would worry about. So in that particular case, it doesn't really matter because the sort of the end thing that we're doing here is really subtraction. So we're going to be looking at decimal places regardless of sig figs and all that. So kind of the smallest decimal place, no matter what you multiply it by, on the front top there is going to be no decimal places. So that's why we would end up the whole number. For questions? All right. So obviously this is just a couple other energy diagrams like we were talking about, energy coming out or coming in. Again, very common in chemistry. That's pretty much how you determine exothermic and endothermic, is looking at the delta H value, and oftentimes it's a lot of times given to you so you can kind of understand what type of reaction you're dealing with. Another really important aspect of heat and energy is what is referred to as specific heat, and specific heat capacity, or sometimes it's referred to as specific heat. Specific heat capacity is the amount of energy that's required to raise 1 gram of a substance by 1 degree Celsius. And that is very similar to the definition of a calorie, lowercase calorie, which is the amount of energy required to raise 1 gram of water by 1 degree Celsius. So there isn't a specific heat equation here. It's in the box there. And we have Q basically is equal to MS delta T. If you kind of rearrange it a little bit. Q here is heat or energy. And usually it'll have units of joules or calories. M is mass, which will have units of grams. S is the specific heat capacity. And that will have units of joules per gram per degree Celsius are calories per gram per degree Celsius. Now, some books, I personally use S because it's just like what I know and what I learned. But some books will use S, some books will use like C for that symbol, and some books will use like SH. So you might see some slightly different sort of symbols, I guess, for specific heat capacity. But personally, for me, I use S for specific heat capacity, and a lot of people do as well. But you'll sometimes see in books, so maybe it's a different letter used for specific heat capacity. The change in temperature here is what we see. It is the final temperature minus the initial temperature, and one of the few places in chemistry where we actually leave it in degrees Celsius. So pretty much everywhere else we go to Kelvin, but when you use this equation, degrees Celsius is typically what you use. And the reason for that is the specific heat capacity is in joules per gram per degree Celsius or calories per gram per degree Celsius. So the specific heat capacity is in degrees Celsius. So you need your temperature in degrees Celsius as well. And by the way, obviously there's no negative on any of this. It's just from PowerPoint. So on either of those. The specific heat capacity of water, which is a value that you should know, is 4.184 joules per gram per degree Celsius. And our 1 calorie per gram per degree Celsius. This is really for liquid water, by the way. Specific heat capacity for ice or steam is actually different. It's about 2 joules per gram per degree Celsius. So it does actually matter in the case of water what state you're in, but most of the time you're in the liquid state, and we use the 4.184. So you definitely should know this relationship. That also ties into a relationship we saw earlier, which is going from calories to joules, and it is the same number. That is the 1 calorie is 4.184 joules. So if you remember that little conversion we saw earlier, is basically the specific heat of water. Now, a couple of things about this equation. When we calculate Q, that is the heat or energy, and sometimes people get that one and the specific heat capacity sort of reversed a lot of times. So again, Q should really only have 1 unit, and the specific heat capacity should have 3 units associated with it. When we do any type of process like this, for example, where we could calculate Q, and if we do it under constant pressure conditions, it will actually give us the delta H value, the enthalpy, change in enthalpy. So if you do sort of an experiment like we're going to do today, where you could just really measure the change in the temperature with some coffee cups. Put a little bit of thermometer in there and measure the temperature. If you do this at constant pressure, basically delta H will basically be the same as Q, basically. So you can actually, just with a thermometer, basically figure out the change in enthalpy of a reaction by just following the temperature change. That is why it is really important in this calculation that you do for the temperature part, final minus initial. As we talked about, if the temperature increases, right, that means that that substance has gained energy, right? And it's going to be positive and endothermic. If we see the temperature of a substance start to go down, that means it's going to be releasing energy, right? And it's going to be exothermic. So when we look at the specific heat equation, it is only the delta T part, or the change in temperature part, is the only thing that can make it positive or negative. So that's why it's important to do final minus initial, because if it's an exothermic process, that will get you your negative sign that you need for your final one. Mass and specific heat capacity are always positive numbers. So that change in temperature is really important to make sure you always do final minus initial. Sometimes people are taught, like I might have mentioned earlier, just to take the difference. And if we take the difference, you always end up with a positive number. So you won't have an idea if it's really exothermic or endothermic. So always important there to do final minus initial. Any questions on that there? If I have a really large specific heat capacity, does it take more or less energy to change the temperature? It takes more energy, and that's what the units of specific heat capacity are, right? Joules per gram per degree Celsius. The amount of energy, which is joules, to raise 1 gram by 1 degree Celsius. So the larger the specific heat capacity, the more energy it has to put in there to change the temperature by just 1 degree. If you had something with a smaller specific heat capacity, you don't have to put as much energy in there to see a temperature change that would occur. So something like water has a relatively big sort of specific heat capacity. So it does take a little bit of more energy than, say, something that had a specific heat capacity of like 0.2 joules per gram per degree Celsius. Any questions on that? All right, so here's a table from your book there, some of the specific heat capacities. And once again, as we just mentioned, you do need to know definitely for liquid water, the 4.184, again, are the 1 calorie per gram per degree Celsius. As I mentioned a second ago, ice and steam, which is also water, as you can see, different values for specific heat capacity. So it does matter really what phase you're in, especially with water there, because, you know, if you're dealing with something that's ice, you would not use the 4.184 number. You would use the more 2 number there. And obviously, if you're dealing with liquid water, then you will use the 4.184. Why is the specific heat capacity of liquid water really important? Well, we could use it to our advantage in a lot of cases because when we do chemical reactions, they are solutions. And solutions are aqueous. And aqueous basically means a water environment. So because a lot of solutions are mainly made up of water and it's sort of a water-based sort of environment, we actually can, without knowing the actual specific heat capacity of what's reacting, we could just assume that it will have a specific heat capacity similar to water. So we could do the calculation really easily. We know the specific heat capacity of water. We know how much mass or reaction would be, and we can follow the change in temperature. So it makes it really easy and convenient with just a thermometer, some coffee cups, and some water. You can basically follow how much heat's either being absorbed or released as a result of a reaction, even if you're mixing solutions that aren't technically pure water or anything like that. But because they're really water-based, we could still use the specific heat capacity of water. So that's why the number is really important. We use it a lot when we do specific heat capacity calculations. As you can see as well, something like gold has a much lower specific heat capacity than obviously water. So again, it would take a lot less energy to see a temperature change difference than it would if you were trying to change water. So why don't you try one here, determine the amount of energy as heat required to take 10 grams of a sample of aluminum that has a specific heat capacity of 0.89 from 25 to 58. Answer both in joules and calories. Okay, let's take a look. So obviously we're dealing with specific heat here. So our specific heat equation we want to look at. In this case, we are looking for Q, which is energy, or heat. We have the mass given to us of 10 grams. We have the specific heat capacity given to us as 0.89 joules per gram per degree Celsius. We have our initial temperature of 25 degrees Celsius, and we have our final temperature here of 58 degrees Celsius. So we pretty much got everything we need on the right-hand side there. So we'll plug it in. That will give us 10 grams times our 0.89 joules per gram per degree Celsius. And again, here we want to go final temperature minus initial temperature. So we do want to take, again, in this case, 58 minus 28. In terms of units, the grams will cancel. The degrees Celsius will cancel. We'll be left with joules, which is good because we're looking for an energy in this case. And a little 10 times 0.89 times 58 minus 25. Going to get us something like 293.7 joules. In this case, we do need to kind of look at sig figs, right? So that's like a 3 sig figs. That's like 2. And here, when we do the difference, there is going to be to the whole number, which is also 2 sig figs, right? So this probably should end up at 2 sig figs in this case. So maybe like a 290 joules will work in this particular case. Any questions on that there? Now we see that the Q value here is a positive number, which means that this is exothermic or endothermic. This is endothermic as it is a positive number. So again, if Q is positive, endo. If Q is negative, exothermic. We also wanted calories, right? So we'll take our rounded number of 290, and there is 4.184 joules per 1 calorie. Here the joules will cancel. So if I take my 290 there divided by 4.184, looks like perhaps 69 calories in this case, right? 69 calories will work in that case. Yeah. Any questions on that there? Okay. So let's take a look at another one here and see. You got 294 joules of heat is transferred to 10-gram sample of silver. What is the final temperature of the silver if specific? Okay, let's take a look. So once again, we got our specific heat equation going on, ms delta T. In this case, we do have Q given to us, which is the 294 joules. Again, it has 1 unit only. We have our mass, which is our 10 grams. We have our initial temperature of 25 degrees Celsius, and we have our specific heat capacity, 0.24 joules per gram per degree Celsius. Again, that is the one with 3 units. So in this particular case, if we put it in, we got 294 joules is equal to our 10 grams times 0.24 joules per gram per degree Celsius. Remember, our change in temperature is our final temperature, right? Which is ultimately what we're looking for in this case. Minus our initial, which is 25 degrees Celsius. Any questions on that so far? Math-wise, we should divide everything to the left first, right? Before we kind of tackle what's in the parentheses. So we basically want to divide that to that side, divide that to the other side as well. And if we do that at this point, 294 divided by 10 divided by 0.24, going to give us 122.5. By the way, grams will be canceled at that point. Joules will be canceled at that point. That will be degrees Celsius equals final temperature minus 25 degrees Celsius. Now, when I did all my dividing, I got some sig fig action happening here, right? So this has got 3, this has got 3, and this has got 2, which means technically my 122.5 should be 2 significant figures, right? So technically speaking, that is sort of where we should lay it up. So since I'm going to continue on with my math here, I'm not going to round. I'm just going to keep the whole number. If you round it at this point, you'll get a slightly different number. But in this case, since I'm still kind of continuing on with the calculation, I'm not going to round, but kind of keep track of, again, where I should be. The last thing I need to do is actually add the 25, right, to the other side. So we're going to add basically the 25 to each side. Which gets rid of it there. And that means that really the last thing I'm doing at this point is adding, which means I should not look at sig figs, but I should look at decimal places, which means my answer should end up at a whole number in this case, which if you just added it without, again, rounding before, you would end up with 147.5 degrees Celsius, which based on our place here, about 148 on the round is what you should get. Now, if you kind of rounded at this point, you would have ended up with 120, right? And you end up about $1.45 there at the end. Either one would have been okay. Personally, again, you probably shouldn't round maybe to the very end to kind of clean it up at the end. But as long as you went to the whole number, you're probably okay either way. Yeah.
Because I was choosing the figures that you're going to put in 25.
Yeah, so remember the last operation we did there is really adding, which falls under the adding and subtracting, which means you do want to look at not significant figures, but decimal places. So since the 25 is a whole number and the other one technically actually should be a whole number anyways, if you really round it at that point, it should have been like 120 and you should end up with a whole number at this point. Yeah. Other questions? And again, if you did round to 120, you obviously end up with 145 versus 148. Again, 148 is probably closer to what the actual temperature should be, and that's why I'm holding off on rounding might be a little better approach here to the end. Any questions on any of that there? Now, let's talk about another sort of aspect of specific heat capacity, and that's really the transfer of heat from one object to the next. And as we talked about, heat does flow from the hotter object to the colder, right? And the same thing happens. And we can use some of this information to our advantage. So for example, if we had, like perhaps what you might do today, a coffee cup of water that has an initial temperature of say 22 degrees Celsius, right? And if we take and we have a mass of that water, which is, we'll just make it up here, we'll call it 85.5 grams. And let's say we had obviously the specific heat of liquid water, which is 4.184. So we got all that information about our water. We also have a piece of metal here. And obviously have water in here. And let's just say we had about 55 grams of the metal. And let's say that the initial temperature here of the metal was like 99 degrees Celsius. And let's see here. We want to know maybe what the specific heat capacity of the metal is, right? So if I take this metal and I heat it up really hot to a high temperature, and then I take the metal and throw it into my water here. That's at 22 degrees Celsius. Let's just say after the metal goes into the water, should the metal temperature go up or down? Should go down, right? Because it should be actually releasing energy, right? So as that metal goes into the colder water, it's going to release this energy to the water, and we should see the water's temperature go up, right? So we got that transfer of energy. So as the metal goes in, right, it is for the metal exothermic, right? It's going to be releasing the energy. For the water, it is endothermic, is going to pick up the energy. So let's just say it goes for a swim, and eventually the water temperature raises to, we'll just go with, I don't know, make up some numbers, see how bad we do at the end, 25 degrees Celsius, right? What would be the final temperature of the metal if it's sitting in that water? It will also be 25 degrees Celsius, right? Because it's sitting in that water. Eventually will come to equilibrate to the same temperatures the water's at, right? So in this type of situation, when you take something that's hot or cold or whatever it may be and put it into another object, when the transfer of the heat and energy is over, since that one object's in the other, they both will come to the same temperature. So in this case, we know the water will end up at 25 degrees. We also will then know that the metal will end up at 25 degrees Celsius, as it should be the same. So what we could do is, in this situation, is we pretty much know everything about water, right? We have both temperatures, we have the mass of the water, we know the specific heat capacity of water. So in our calculation here in this example, we could figure out how much energy the water is going to absorb in this case, right? Because the metal is hotter. So we could use our specific heat equation for water. And if we do it for water, which is our MS delta T, and we'll see how bad my made up numbers are here. So my MS is going to be 85.5 grams. Our specific heat capacity of our liquid water going to be 4.184 grams per degree Celsius. Once again, here we're going to do final minus initial. So we'll do our 25 minus our 22 degrees Celsius. Degrees Celsius will cancel, grams will cancel, we will end up with 85.5 times, maybe here, times 4.184 times 25 minus 22. Which will end us with about 1,073.196 joules. Now, for following sig fig rules on this, we do have 3 sig figs, right? We got 4 sig figs. And when we subtract here, we would go to the whole number, which in this case is only 3, which actually is 1 sig fig. So technically speaking here, our energy should actually be 1 significant figure in this case, which would be, we'll call it about 1,000 joules of energy. This number here is the amount of energy that the water has picked up. And the sign that we see on the water value here for Q is positive or negative. It is positive, which makes sense, right? Because that's what we expect to happen. It's endothermic. Now, all the energy that the water gained in this particular case, all that energy came from what thing? It all came from the metal, right? So that's the only thing that you dumped into the water that had any kind of heat difference, right? Or that would allow it to gain it. So because all of the energy came from the metal, there's the sort of law of conservation of energy, which means if somebody loses a certain amount of energy, that should be the same amount of energy that somebody gains. So we could use that relationship of, sometimes it's referred to as, if we're doing it with a metal, the Q of the metal equals minus the Q of water, which means the Q of the metal in this case would be negative 1,000 joules. And that is because for the metal, it is exothermic. So the amount of energy gained by the water is the exact same numerical value as the amount that was lost by the metal. The difference, though, is the sign is going to be negative to imply that it is exothermic for the metal. Any questions? Yeah. We have the negative because it's really like an opposite relationship in a sense. So if somebody is releasing a certain amount of energy, which would be like a negative process in terms of energy for them, it's going to be a positive absorbing situation for whoever's gaining that energy. And so that's why there's got opposite in sign, and that's why the negative's there to kind of reverse the sign. It would be the same situation, for example, let's say that the metal that we took was actually colder than the water that we put it in. When I would take the metal and put it into the water, which one would lose energy, which one would gain energy if the metal was actually colder than the water? The water actually would lose energy, right? Because it is hotter than the metal. So it's actually going to transfer its energy to the metal. We would actually see the metal's temperature go up, right? Water's temperature go down. In that situation, it works the same way. For the water, it'd actually be exothermic, right? Which means it's a negative value of Q you would get. So with that negative sign, 2 negatives make a positive. And that would mean that the metal is going to be absorbing that energy and be positive. So you need that sort of opposite relationship. And that's what the negative sign sort of gives you. So you can see it works the same regardless of one's hotter or one's colder. It doesn't really matter. But you do need to incorporate that negative sort of sign to change the energy value. We're going from one to the next. Other questions? All right. So why this is important now is if we look at our metal and we take the specific heat equation for metal, which is ms delta T, we now have Q. We have our final and initial temperatures, which is the change, and we have our mass, which means we now have all the numbers that we need to figure out the specific heat capacity of that metal by rearranging the equation. And if we do that, S would equal the Q of the metal divided by M and delta T, basically taking both of these guys and dividing it to the other side. So when we put our numbers in there, it's going to give us minus 1,000 of my made up number. We're going to now use the mass of the metal because we're looking for the metal here. And that is our 55 grams. And this is also an important part for the metal. In this case, in any case, we want to do final minus initial, which means I actually should be taking 25 minus 99, right? So in this case, for the metal, the final temperature is 25. It started at 99 degrees Celsius. That's important because this number here will give us what type of number? Give us a negative, which goes with our negative for our energy, which will turn our specific heat capacity into a positive number, which is what they should be. So that's why it's important to, again, do the final minus the initial to make sure you keep the negative where it needs to be, because those things will work out correctly, hopefully, for you if you do that. So if we do the math there, it looks like 1,000, we'll use our rounded number there, 55, and divided by 25 minus 99. And that's going to give us, in this case here, something like 0.245. The units are joules, grams, degrees Celsius, joules, grams, degrees Celsius. And now specific figures wise, really, with my bad made up numbers, we're going to end up with really one sort of significant figure, because I made up those numbers. So based on sig fig rules, we would have one on top and obviously divided by 3. And then when we do the subtraction, we have 2, because it should go to a whole number. So basically we should end up with 1 in this case. And again, all 3 units stay. The number stays with the joules part or the calories part if you're doing that. And it's always per gram per degree Celsius. Any questions on that calculation? So in this type of thing, much like the lab we're going to do today, just simply using a thermometer and following the change in really the water, we could relate it to how much energy was gained or even lost by the water in certain situations. And then we could sort of relate it back to, whatever we kind of threw in there into that water. Any questions on that? All right. So this is what we were just talking about. And again, this is sort of a setup here. The sort of conservation of energy is that perfect exchange of energy. And the way we get a negative is you basically kind of subtract all that to the other side, and one of them becomes negative, basically. So if you just remember, the Q of the metal is equal to minus Q of the water. That's essentially this. Again, all this travels to the other side, which makes it negative, and that's how the negative gets incorporated into there. All right, so why don't you try one here? We take a 110 gram sample of a metal at 55.5, raises the temperature of 150 milliliters of water from 23 to 25.5, determine the specific heat capacity. Okay, let's take a look. So it's kind of the same situation. We got some water. We got 150 milliliters of water. And we know that the initial temperature of the water there is going to be 23. We know after the metal goes for a swim, it's going to be 25.5. And we also, because it's liquid water, know the specific heat capacity of it is 4.184 joules per gram per degree Celsius. So again, we have a lot of information for our water. We also have some information for the metal that's going in. So we have our metal here, and it has a mass of 110 grams. It has an initial temperature of 55.5. We know that once it goes for a swim in the water, it should also end up at the same temperature as the water, right? When it kind of heats up. So we know that the final temperature of our metal is going to be 25.5 degrees Celsius. Again, the same stopping spot as the water in this case. We are looking for the specific heat capacity here of the metal. So if we think about our Q for our water, we do have almost all the information we need, except that this is in the wrong units, right? So that is our volume, but we need the mass of water. And we know that the density of water, right, will allow us to do that. Density of water is 1 gram per milliliter. That is something that you should know, as we talked about, yes. So using the density of water here, D is equal to M over V. Mass would be volume times density, which would be 150 milliliters times our density value here. And that's going to give us 150 grams of water in this case. We're not going to look specifically at the sig figs and that density value again, because some people use 1.000 and so forth. So we'll just use it as an exact sort of conversion there. In this case, we now have everything that we need to figure out the amount of energy for the water. And that energy, is that energy being absorbed by the water, or is it releasing energy in this case? The water should be absorbing the energy, right? Because again, our metal here is starting at 55 degrees, which is hotter than our 23 degrees that our water started at. So the energy transfer, the heat transfer here is going to go from the metal that's hotter into the water that is cooler. And that's why we see the water's temperature increase in that situation. So here we'll do our Q for our water. And that would give us our 150 grams, or 4.184 joules per gram per degree Celsius. Again, we're going to do final temperature minus initial in this case. Degrees Celsius cancel, grams cancel, leaves us joules, which is good. We got so we end up here with about 1,569 joules. Sig fig wise at this point, that's got 4, right? That's got 4. When we do the difference here, that is like 2.5, right? Which is 2 sig figs, right? Which means technically speaking, that is about where we should end up at that point. Again, here, I'm probably going to hang on to the whole number because I'm going to continue on, obviously, and use it in the calculations. But again, we do want to kind of keep track of it. Technically, if we were ending the calculation at this point, 1600 is where we should have for that. We do see that our Q value is positive, which means it's endothermic, which is what we expect to happen when we throw the hotter temperature into the water. Now our relationship between the water and the metal is that negative relationship, which means Q of the metal would be negative 1569. And again, I'm hanging on to kind of all my numbers there. And now that we have the Q of the metal, which is exothermic and negative, again, same value, we have everything that we need to solve for the specific heat capacity of the metal. So if we take our Q of the metal is our ms delta T, solving for S would give us our Q of the metal divided by m delta T. Put in our numbers, minus 1569 joules divided by our mass of our metal, which is 110 grams. And again, here, the important part, we want to do final minus initial on our temperature for the metal. So our final temperature of our metal is 25.5 minus our initial, which was 55.5 degrees Celsius. And if we do that, we will end up with here 1110 and so we will end up with looks like go up here 0.48. Again, the units here do not cancel, so joules per gram per degree Celsius as their specific heat capacity. Again, we will get a negative as a result of that, which will take that negative and turn this into a positive. Sig fig wise, remember, that's where we really should be, which means that has 2 sig figs. This has 4 sig figs. And when we do the subtraction there, was that about 30.0, which would be 3 sig figs as well. So again, that's why we end up basically with the 2 sig figs based off of the kind of the first part of the calculation in this case. Any questions on that there? So this is a very, very common sort of procedure that's used, like monitoring really the change in water to really figure out what is happening in terms of energy change. And again, like I said, we could also use this method if it's not just like throwing a solid into water, but mixing 2 actual reagents or solutions together because they're aqueous and water-based. You could do the same thing. You could get the mass when it's all mixed together, of the solution. You get the change in temperature. You use the specific heat capacity of water and figure out, again, just mixing two reagents together in your coffee cup, how much energy is absorbed or released in that reaction. Why do I keep talking about using coffee cups? Coffee cups are insulated, right? So that would allow no heat loss to the surroundings or anything like that. So it keeps it all sort of very nicely insulated. And a very cheap coffee cup can be used to do some good chemistry by basically pouring everything into it, and it keeps it really well insulated when this reaction takes place, that we're not going to be losing any heat to the outside of that reaction. Any questions on that? All right. So to finish up on this chapter, a couple other things about energy and nutrition. I think we touched upon it earlier. There is another sort of calorie, which again is sometimes referred to as a nutritional calorie, and that has a capital C. And one of the capital C calories is 1 kilocalorie, or 1,000, once again, of the lowercase c's there. A calorimeter is an apparatus that's used to measure, for example, the calories in food. They're sometimes referred to as bomb calorimeters because basically you put your cookie in there. In this pretty isolated container. You have basically water all the way around, a thermometer. You have wires. You basically set it on fire and let it burn. As it's burning, it's obviously going to transfer energy from, say, your cookie, right, to the water in the outside. And doing a very simple calculation like we just did using the specific heat capacity of water and the specific heat equation, you can figure out how much energy is being released, say, by your cookie, which you can then translate into how many nutritional calories that would be. And that's how they get those things that you see like on the back of your packages, you know, caloric or calories there is in a food item. Years ago, we used to do an experiment very similar to that. You could take like an old Coke can that's empty, put some water in it. Underneath it, you could take like a Cheeto or something like that, set it on fire, and as they heat it, it will heat the water that's in the can. So all the energy is coming from, you know, you're burning Cheeto or peanut or whatever it may be. And you can very simply, just with a thermometer, figure out how much energy is being released. Now, when we talk more specifically about sort of calories, there's really three basic types of calories or caloric values that we look at, and that's carbohydrates, fats, and proteins. And each of these have what is referred to as a caloric value. So 4 kilocalories for carbs, 4 kilocalories for proteins, and like 9 kilocalories for fat. And if you ever look on the back of a nutritional label on any type of food, you will see those three categories listed as to how many grams of each of those are in there. So a kilocalorie, once again, is basically a nutritional calorie, right? So if you know how many grams of carbohydrates you have, fat, and protein in a food sample, you can multiply it by each of those and add them together, and that'll give you how many calories are in your food item. So for example, by doing so like so. So, you know, if you had something that was, anybody have anything? Candy bar, chips, something that has a label? Yeah. Just tell me, is it on the back tell you how many carbohydrates you have? How many grams? 20. And protein? 3. And fat? 8. Okay. So if you look on the back, you can get those grams. And then basically what you would do is we would, for our carbs, we would times it by our 4 kilocalories per gram. For our protein, we would times it by its caloric value of 4 kilocalories per gram. And for our fat there, 9 kilocalories per gram. And if we do that there, that's going to give us 80 kilocalories. We'll have 12 kilocalories. And we'll have our 9 times 8, which would be 72 kilocalories. Which means if we just add all those together, 72 plus 12 plus 80, there's approximately 164 kilocalories our calories in that sort of thing. What does it say on top? What does it say the total calories are on that per serving? 160. Yeah, they usually round down for some weird reason why they would do that. But that's basically how they get that number, is by taking the grams of each of those things. And that will give you how much there is obviously per serving and stuff like that. Any questions on that there? All right, so most of the time in chemistry, this is sort of what we use, like we're going to use today. And this again is what is sometimes referred to as a coffee cup calorimeter. And a coffee cup calorimeter, as I mentioned earlier, works really well because it's fairly well insulated. We don't lose a lot of heat or energy to the surroundings. And by just simply using a thermometer and following the change in temperature, again, you could basically figure out things like how much heat or energy is being absorbed or released in a reaction. And when you do this at constant pressure, which is typically what we do, everything at the pressure of our room doesn't really change all that much. So it's, sort of done at constant pressure. When you calculate Q in that equation that we've been using, it will equal the delta H at constant pressure. So you can get the change in enthalpy by just simply doing an experiment like we're going to do today. You could actually get it joules per mole or kilojoules per mole if you know how much you are reacting. So if you threw in there maybe 50 grams of magnesium with some HCl and you had your thermometer in that coffee cup as it's all reacting, you can follow the change in temperature. And again, because HCl is also water-based, we could use specific heat capacity of water. You could also figure out how many moles of that it would be, and you could get how much kilojoules per mole, which is a typical unit that you see for delta H. And you could calculate the change in enthalpy by simply just using coffee cups and thermometers. Any questions on that there? All right, we won't go over this example. It's kind of like the one we just did with the wrapper over there. But again, if you had this many grams of carbs or fat or protein, you could basically just multiply each of them by their caloric value and then add them together. And obviously that will give you how many calories there are per serving. The last thing we're going to talk about in terms of energy is a little bit about sort of delta H and change in enthalpy and what happens if we are doing it for, say, more than one or something like that, or a little bit different than the coefficients that we see in the equation. So for example, if we have this equation, our coefficients, which are not written because they're ones, are 1. And basically what this means is these coefficients can be thought of as moles. And basically what that would mean, in 1 mole of ice, you will need 6.01 kilojoules of energy to go from basically solid to liquid. This is basically what is known as the heat of fusion, which is the energy required to change something from solid to liquid. And that's what this is actually known as, the heat of fusion. And that is the energy to go from solid to liquid or liquid back to solid, which, by the way, occurs at the normal melting point, freezing point. So for water, that's 0 degrees Celsius. At exactly 0 degrees Celsius, you have both liquid and solid happening at the same time. But it takes a certain amount of energy to do nothing more than move something like ice at 0 degrees to liquid water at 0 degrees, not change the temperature, but change the state of it, and that is the heat of fusion. And for water, it's actually that number right there. The 6.01 value is the heat of fusion. It does change for different substances, but that's a common one. That is roughly about 335 joules per gram that is needed to change basically ice into liquid water at 0 degrees Celsius, or liquid water at 0 degrees Celsius back to ice. By the way, just for comparative sake, if we were to look at water, liquid water going to steam, which occurs at 100 degrees Celsius, right? And the same thing at 100 degrees Celsius for water, which is the normal boiling point of water. There is a certain amount of energy required to do nothing more than take liquid water at 100 degrees Celsius to steam at 100 degrees Celsius. So not change the temperature, but just change the phase. And that is what is known as the heat of vaporization. And for water, that is roughly 2260 joules per gram, or about 40 kilojoules per mole, give or take, 40.5. And that is the energy required, again, to go from liquid to gas or gas back to liquid. Which one takes more energy? Which transition? The one that goes from liquid to gas, right? It takes about 2200 joules of energy per gram versus about 330 going the other way. And that's because as we go from solid to liquid, everybody's still relatively close to each other, right? But when we go from liquid to gas, they have completely broken apart from each other, right? They're flying around in the gas stage. It takes a lot more energy to do that transition of going from liquid to gas or backwards. So this does tie into our specific heat that we've been talking about a little bit. And the idea here is this: if we're doing something where the state is the same, but the temperature changes, we want to use our specific heat equation, which is Q is equal to ms delta T. If we're doing something where the state changes, but the temperature stays the same, that is going to be your delta H of fusion, which would take you from solid to liquid or backwards, or your delta H of vaporization, which will take you from liquid to gas or backwards. So these two things can be used together in terms of a calculation. For example, if we took like ice at 0 degrees Celsius and we took it all the way up to steam at 100 degrees Celsius, there's many stages that occur as that process happens. So for example, if we looked at it like a heating curve or something like this, let's just say that that is steam up here, that is liquid water, and that is ice. And this would be 0 degrees Celsius. This would be 100 degrees Celsius. So let's say we started like right about here, and we had ice at -2 degrees Celsius, and we wanted to take it to steam at 100 degrees Celsius. And we want to know pretty much all the heat that's required to do that. It actually happens in several steps. The first step that would happen is we would have to take it from ice at -2 degrees Celsius to ice at 0 degrees Celsius. Try it that way. And that is the same phase, right? That is ice to ice, right? It's all the same phase, but we're changing the temperature. To clear out the energy, we would use the specific heat equation. Important in this step, right, would be, should I use the 4.184 number for water? The answer is no, because that's not liquid water at that point, right? That is the ice value for water, specific heat capacity. That's like that 2 number that we saw in that table. So you would do the exact same calculation that we did, final minus initial, which, by the way, in this case, final would be 0 minus our initial -2, right? So that's what you would do there. You would want to use the specific heat capacity of ice. The next thing that would happen actually is, now that we're at 0 degrees Celsius, this is where the phase change occurs. And that happens at the exact same temperature, as you can see by the flat line, right? The temperature is not changing, but the state is changing. That is where we would incorporate our delta H of vaporization. So for example, if we had a number for the second step, we would take the mass of our water. We would times it by, which normally would be in grams, the heat of vaporization for water, which is like 335 joules per gram. That will give us how many joules it takes to not really change temperature, but take it at 0 degrees solid to 0 degrees liquid. Any questions on that? So the first part of this, we're changing the temperature, but not the state. The second part, the state is changing, but not the temperature. So that's a phase change where we'd use something like the heat of fusion. Yeah. So there is a certain amount of energy to do that, it will change the phase, but there's not enough energy to actually see a temperature change until you continuously put more energy in there to do it. And that goes back to the sort of specific heat capacity, right? There's a certain amount of energy that's needed to kind of really see that change. But again, there's a certain amount of energy really just to kind of keep it that. So all phase changes for substances occur at the same temperature. And at that temperature, they're in equilibrium with each other. So they kind of go back and forth. And you kind of have to put enough energy there to kind of keep it going in one direction, or remove enough energy to kind of get it going in the other direction. Now, what we would be doing at this point is we're sitting here at liquid water at 0 degrees. We would then need to take it all the way up to liquid water at 100 degrees Celsius. So the third step here would be liquid water from 0 degrees Celsius, 0 degrees Celsius, to liquid water at 100 degrees Celsius. That is liquid water all the way through that, right? And the temperature change. So we would go back to our specific heat equation. At this point, should we use the 4.184 number? We should, because now we're at liquid water, right? All the way through that. So that is the specific heat capacity for liquid water. So when we go into the Q equals MS delta T at this stage, we would use it for liquid water, which is the 4.184. The last thing that we would want to do is another phase transition, which is taking it from liquid water at 100 degrees to steam at 100 degrees Celsius. And that's going to be our delta H of vaporization. I'm sorry, I think I wrote the wrong thing down here. That's actually the delta H of fusion down there. Sorry about that. It's the right number, just the wrong label. The delta H of vaporization will take us from liquid to gas. And again, we're not changing the temperature, but we are changing the phase of it. So the fourth step that we would do is use the delta H of vaporization. We would use our mass of our water in grams, times it by the 2260 for water, and that will give us how many joules of energy is required to take it from now liquid water at 100 degrees and do the phase change to steam at 100 degrees. The total amount of energy to do all this can be found by adding up all 4 of those steps. So you'll get an energy number for each of those steps. If you did the calculation, the total amount of energy would be step number 1 plus step number 2 plus step number 3 and step number 4. By the way, going from ice to steam, when we do all these calculations, all of our energy values should be positive or negative. They all should be, as we go from ice to steam, it's exit. It is endothermic. So we should have positive numbers at all 4 of those steps. By the way, if we started at 100 degrees Celsius for steam and went the other way and ended at ice, the only thing that should change is the sign. Yeah, you'll end up with the same numerical value coming backwards, but it's exothermic. So instead of positive 335, that would be negative 335. Instead of positive 2260, it would be negative 2260. Instead of 0 minus minus 2, it would be minus 2 minus 0, right? Coming the other way. And you'll end up with a negative value. So there'd be exact same amount of energy, but it would be negative coming down. Any questions on that there? That was a real tangent move right there. But just to finish up on this, and we probably won't come across too much, if we do have a delta H value for a particular reaction given to us, if we do change the coefficient, say we needed 2 of everything, what we do with our delta H is actually multiply it by 2, which is what we see down here. So, sometimes you may need to multiply a reaction by a certain coefficient, and then you would multiply the delta H. Also, if you ever needed to reverse the reaction, the thing that changes is the sign. So as we can see here, instead of going from solid to liquid, if we would need to go from liquid to solid, same number, just the sign of delta H changes. So if you ever have to do the opposite sort of reaction that you have, the delta H value will change the sign. Any questions on any of that there? All right, that wraps up actually chapter 10 that we're going to talk about. You